Welcome to this Advanced Intelligent Resilient Framework, or IRF video. This video is part of a series of videos discussing advanced IRF and are available on the HP website. So how is the master device elected in an IRF system? It's not based on the member number. In this example, the master device has a member ID of 1, but it doesn't have to. Member 2 could have been the master. So the master is determined as follows. It's done via an election process where the current master wins, even if a new member has a higher priority. So let's assume for the moment that this switch had a priority of 30 and is currently the master, and a new switch is added to the topology and has a priority of 32. The current master will stay the master, and this switch member 3 would become a slave or standby device. The default priority is 1, but when you create a new IRF system, the highest priority wins. So when initially configuring an IRF system or virtual device, this first step is skipped because there is no current master. Then it's done on priority. So if we had a new IRF system consisting of 3 switches, let's say for instance that there are multiple cables here, this switch had a priority of let's say 30, this switch had a priority of, let's say, 20, and this switch had a priority of, let's say, 10. This switch would become the master switch because it has the highest priority. Now, if the first criteria cannot be used because there is no current master and the priorities are the same, let's say, for example, the priority of these 2 switches is set to 1, which is the default, then the longest uptime is used to determine who the master device is. The precision interval for the system uptime is 10 minutes, and this information is transmitted in IRF hello messages sent between the switches. If that can't be used to determine who the master is, let's say both switches come up within a few seconds of each other, then the lowest MAC address is used to determine who the master unit in the IRF system is. It's not good practice to use longest uptime and lowest MAC address when determining the master in the IRF system, so it's better to set the priority on your devices when forming a new IRF system. Now there's a separate video in this series that demonstrates the various options here. So you'll see an example where the current master wins, an example where the highest priority wins, an example where the longest uptime wins, and an example where the lowest MAC address wins. Once again, you want to use this criteria rather than these when creating a new IRF system. And also be aware that the current master will win. So once again, even though you add an additional device to the IRF system that might have a higher priority, the priorities are on the range 1 to 32. So let's say, for example, that you have the priority of this switch set to 30, this switch set to 20, and a new switch joins the IRF system or IRF stack with a higher priority. This switch will remain the master because it's the current master. However, if it was a new IRF system, then this switch would become the master because it has the highest priority. And what happens when the master goes down? Let's assume for the moment that this device on the left is the master. It has a priority of, let's say, 32. This device on the right is the standby device or slave device and has a priority of 30. These ports are connected as IRF ports, and this is an IRF system. What happens when the master device goes down? So when the master device goes down, the standby device will become the new master because it's the only device available. Let's say you rebooted the master, so it wasn't a physical failure, it was just a reboot. When the master goes down, the slave becomes the new master device. When the master comes back again and rejoins the IRF system, it will now rejoin as a standby device and not as a master device. This slave device or standby device became the master when the master went down. So it's currently the master when this previous master device joins the IRF system. So the current master wins. So because the switch on the right is currently the master, when the switch on the left went down, it will remain as the master device, and the roles will change in this example. So now member 2 is the master device, and member 1 is the standby device. Now, videos in this series use the HP simulator as much as possible. Using the HP simulator allows us to demonstrate IRF technologies quickly, as well as allowing you to download the HP simulator and practice the configuration yourself. Now, this depends on what you're using to view the videos, but as an example, if you're viewing this via a Brainshark, you will find the HP simulator configuration attached to the Attachments tab of this presentation. So download the HP simulator, which is available for free from the HP website, use the attached topology, and then you can follow along by doing this yourself. This is the IRF HP simulator setup, which consists of 4 core IRF switches, as well as 2 Access IRF switches and a MAD Assist IRF switch. In the HP simulator setup video, which is part of this series, we explain how to download, configure and set up this environment so that you can test and experiment with the HP IRF technology. So once again, in this demonstration, we're going to look at the master election process. So firstly, the current master remains master. So if a new device is added to an IRF system, when that device boots and attempts to join the IRF system and finds an existing master, it doesn't try and take over the master role. The current master remains the master. The new device simply joins the IRF system as a standby or slave device. In the second scenario, if there is no current master, so let's say we have a system with no masters, or we have 2 separate IRF devices that join an IRF system at the same time. In other words, they both think they're the master. Then the master for the IRF system is determined by the priority of the individual devices. So for example, if we have switch 1 and switch 2, and they create a new IRF system, the switch with the highest priority will win. In the previous video that's part of this series, we demonstrated an example where one switch had a priority of 32, and the second switch had a priority of 30, and the first switch with the highest priority became the master of the new IRF system. So what about the scenario where there are no masters? In other words, 0 masters. So as an example, you might have an IRF system with 4 members or 4 units, and the master device fails in that IRF system. That means that you're left with 3 devices which are standby devices or slave devices. There is no current master. So those 3 slave or standby units will then compete to become the new master of the IRF system, and the device with the highest priority would become the new master. We also have a scenario where 2 devices are their own masters, and this could happen as an example when 2 devices are booted without physical connections. So during their own boot process, they don't find an existing master and become the master of their own partition. So 2 physical switches, not connected, boot up, and we end up with a situation of 2 masters, 1 master in each partition. When you connect those 2 devices together, the device with the highest priority wins. And once again, that's what we saw in the previous video. In the third scenario, system uptime is the determining factor. So if 2 switches have the same priority and are competing to become the master device, the system uptime is used. In the fourth scenario, if the system uptime of both switches is within 10-minute range, the lowest MAC address will be selected as the determining factor. So once again, first criteria is current master remains master. In other words, the current master wins. Secondly, highest priority wins. Thirdly, system uptime is used. And fourthly, lowest MAC address is used as a tiebreaker. We'll now look at this procedure. In the current system, using the command display IRF on unit 1, we can see that it's currently the master and it has a priority of 32. Unit 2 has a priority of 30, which is lower than the current master device. So we'll now power off unit 1. And now that Unit 1 is powered off, we can see that Unit 2 has become the master device with a priority of 30. So what happens when Unit 1 joins the IRF system again? Remember that Unit 1 has a higher priority than Unit 2. Unit 1 has a priority of 32, Unit 2 has a priority of 30. Currently, Unit 2 is the master device. Because we stopped Unit 1, we need to reactivate the console session. So once the boot process has completed, we can see that a new board has been added. The batch backup has started and has finished. So that completes the IRF boot process. So what does the command display IRF show us? We can see in the output that Unit 1 has joined as a standby device, even though it has a higher priority. So this proves that the priority value is only applicable in the case where there is a competition to select a new master. The current master, Unit 2, remained the master, even though it has a lower priority. So what about the second check, highest priority? This can be verified in the situation where there is a network partition. So in other words, the two IRF units or systems are split or separated from each other. So to simulate that situation, we'll simply shut down the IRF ports to partition the two devices. So we'll go to the physical IRF port, in this case interface 10 gigabit 108, and we'll shut down the interface. We can do something similar on Unit 2, go on to interface 10 gigabit 207 and shut down the interface. So now when we go on to interface 10 gigabit 207 and we enable this interface, we can see that it's device 2 that's rebooted because it lost the election based on criteria 2. Switch 1 has the highest priority, not switch 2. We can now see that Unit 2 is joining as a slave device. We can see messages such as board state normal on slot 2. This process actually shows both criteria 1 and criteria 2. When Unit 2 joins the IRF system, it discovers a current master and therefore immediately joins as a slave. Unit 1 remained up as a master device and therefore is the master of the current IRF system that Unit 2 is trying to join during the boot process. So using the command display IRF, we can see that member 1 is the master and member 2 is the standby device or slave device. So this is a demonstration of criteria 2, that highest priority wins. The next criteria is based on system uptime, and that's when the priority of both systems is the same. We can use the display version command to see the current uptime. We can see that the device uptime is currently 46 minutes. And using the same command on Unit 2, display version, we can see that the current uptime is currently 47 minutes in this example. The uptime is actually the same on both systems because when we connect to the console or auxiliary port, those ports are handled by the same master device. So all the commands, even though typed on Unit 2, actually show the output of the master device, in this case Unit 1. So all the commands that are executed on Unit 2 are actually processed by the master device. So to simulate this properly, we need to create a split brain and separate these two systems to show the difference in the uptime of the two systems. The master device is Unit 1, so we need to shut down the interfaces on this side of the link. So going to interface 10 gigabit 108, we can shut down the interface. And this once again creates two separate IRF systems or partitions. And we can verify that by using the display IRF command. So notice on Unit 2, it's currently the only unit in the IRF system, or only member in the IRF system. And the same is true on member 1 or unit 1. It's the only member of the IRF system, and it's also the master device. These two devices have been partitioned. In this example, we'll change the priority of the second unit to 32 to make it the same as the priority of unit 1. So to do that, we use the command IRF member 2 priority 32. This ensures that we have a priority conflict with both devices having the same priority. So now something else needs to be used to determine who the master is. So once again, we can use the display version command to see system uptime. At the moment, they both have a system uptime of 48 minutes because that time was inherited from the master IRF system. So to ensure that we have different uptimes, we'll reboot Unit 2 while the links are down. That means that Unit 1 will have a longer or greater uptime than Unit 2. Before rebooting System 2, we'll save the configuration. We'll use Save Safely Force. We need to save the configuration so that we have the correct priority configured on this device of 32. And now we'll reboot System 2. Once the reboot has completed, we'll end up having two IRF systems configured with the same priority. The determining factor used in the election process when they are joined back together again is the system uptime. That's the only difference between these two devices. They're both currently master devices and they both currently have the same priority. Now Unit 2 will take longer to boot this time round because once the IRF ports are configured, during the boot process it has a built-in wait timer which is used to attempt to detect an existing master system to ensure that if multiple systems are booted very quickly after each other, it doesn't select the wrong master. In this video, we'll speed things up to stop you getting bored, but be aware that the boot process may take a while. So now that Unit 2 has booted up and completed the startup process, we can verify the IRF configuration. And in this case, we can see that it's become the master device with a priority of 32. Using the command display version, we can see the uptime. In this case, it has an uptime of 2 minutes, which is a lot lower than the uptime of Unit 1, which is about 51 minutes. So when we enable the physical links between these two IRF systems, we should see that Unit 2 loses the election, even though it has the same priority as Unit 1, because it has a lower uptime. So in other words, Criteria 1 cannot be used because they're both master devices. Criteria 2 cannot be used because they both have the same priority. So Unit 1 should win because it has the highest or longest system uptime. So hit enter, and as you can see, Unit 2 immediately reboots. In this example, the boot process will be quicker because during the boot process, it finds a master device on the link, which is currently enabled. Once again, because of the reboot, Unit 2 will use Criteria 1, and it will join as a slave device because it finds a master device when it joins the IRF system, so it'll join as a slave. We can see that once again by using the command display IRF. As you can see in the output, Unit 2 or Member 2 is currently a standby device or slave device, and Unit 1 or Member 1 is the master device. So this demonstration shows that system uptime is used as the third criteria for determining the master device in an IRF system. The last resort criteria used is lowest MAC address, and that would be used when we have two masters, the priorities are the same, and the system uptime is the same. The MAC address used is the base system MAC address. So to demonstrate this, we need to create a partition of two devices, and to do that, we'll shut down the link between the two systems. We want to ensure that the link remains down during the reboot, so we'll save the configuration of Unit 1. So both systems have the same priority, and now we need to ensure that they both have the same system uptime. So to do that, we'll reboot both systems. However, before doing that, to ensure that the reboot takes the same amount of time on both systems, we'll also shut down 10 gigabit 207 on Unit 2. That means that Unit 2 won't try to detect an existing master because the IRF ports are shut down, which means that the boot up or startup time will be similar for both systems. So let's reboot both systems using the reboot force command. So once again, both Unit 1 and Unit 2 are being rebooted, and that ensures that they have the same uptime. We can now see that both Unit 1 and Unit 2 have rebooted. Using the command display IRF, we can see that they are both masters of their own partitions. They both have the same priority, and we can use the display version command to see that they have a similar uptime, in this case of 0 minutes. We can also use the display IRF command to view the CPU MAC address, and here we can see that there's a difference because Unit 1 has a MAC address of 00E001, while Unit 2 has a MAC address starting in 00E002. That therefore means that Unit 1 has a lower MAC address in this example, because Unit 1 has a CPU MAC address starting in 00E001. So when we enable the IRF ports on both sides, so we'll use the undo shut command to enable 10 gigabit 107 on Unit 2, firstly, and then save the configuration. If we don't do it in this order, when Unit 2 joins the IRF system, it will reboot, but the saved configuration at that point would have the interface down, so we need to unshut the interface first, then save the configuration, and only then enable the interface on Unit 1. So now that Unit 2 has the interface enabled and configuration saved, when it reboots, it will reboot with the interface enabled. So now we can undo shut the interface on Unit 1. This unit should win the election, so when we hit enter, we can see that Unit 2 reboots, so it's done what we expected. So once again, as soon as we enabled the interface, the IRF protocol determined who the winner was, in other words, who the master device is. In this case, Unit 1 won the election because it had the lowest MAC address. Unit 2 lost based on MAC address, so it rebooted. Now once again, the reboot process is quick on Unit 2 because when it reboots, it finds an existing master and immediately joins as a slave. So as you can see, once again, batch backup has started and is finished. We can use the display IRF command once again to view who the master and slave is. And in the output, you can see that Unit 1 is the master, Unit 2 is the slave of this combined IRF system. So in this demonstration, we reviewed the full IRF election process based on current master winning, or highest priority, or system uptime, or lowest MAC address. However, in the real world, you shouldn't rely on that process. You should make sure that you never end up basing the election on system uptime or lowest MAC address. This is only shown here for completeness. You should always make sure that the current master wins and that the highest priority is configured on one of your devices. So in this example, we'll rectify the configuration by making sure that IRF member 2 has a priority of 30, which is lower than the current master, but higher than the default configuration. So best practice, make sure that you have one device with the highest priority. Other devices have priorities greater than 0, but different priorities don't rely on system uptime or lowest MAC address for master determination. Make sure that your priorities are higher than the default, but lower than the priority of the master. So we'll save the configuration at this point for the subsequent videos that are part of this series. That concludes this video discussing Advanced IRF. This video is only one of a series of videos discussing Advanced IRF configurations. Please look on the HP website for additional videos to help you configure and troubleshoot HP IRF. Thank you for watching.